Good evening, students. Today we are going to see a valence bond theory and their limitations also. Okay, and their limitations. What is the useful of this valence bond theory? What we can able to find out, okay, from the valence bond theory. From the valence bond theory, a few things we can able to find out. First thing is hybridization. What type of hybridization we can able to find out? And the second thing is not only the hybridization, with the help of that we can able to find out the magnetic property. Second one is magnetic property. Magnetic property means whether it is a diamagnetic or paramagnetic. And the third thing is whether it is a low spin or high spin complexes. We can find out a low spin or high spin. With the help of this, we can able to say inner orbitals or outer orbitals. Whether the complexes inner orbitals or outer orbitals. These things we can able to find out with the help of valence bond theory. The valence bond theory we can otherwise we can say it as a VBT theory. Okay, let us see about this. Okay, the first example which I am going to explain over here is the first complex which I am going to take is cobalt ammonium complex. Okay, this is the cobalt ammonium complex. For this, how to find out the valence bond theory, how to find out the hybridization, everything. I'm going to explain some of the tricks behind in that. Okay, what is the tricks? What is the way we need to find out? Easy tricks I'm going to say. First one, we need to find the oxidation state of central metal atom. Okay, this central metal atom. Here the central metal atom is cobalt. Generally I'm saying the central metal atom, oxidation state of the central metal atom. First thing. Second thing, electronic configuration. Second step is electronic configuration of that central metal atom. And the third one, whether the ligand is weak field ligand or strong field ligand, that you need to find out. Whether the ligand is weak field ligand, or strong field ligand. These things we need to find out. Okay, this is the main three tricks which you need to keep it in your mind. With the help of these three tricks, we can able to find out hybridization, magnetic property, and whether it is a inner orbital or outer orbital. Let us see the first one. What is that? Oxidation state of the central metal atom. Here the central metal atom is cobalt. How to find the oxidation state? First we are going to do the oxidation state. Okay. First. So cobalt only we are going to find out. Oxidation state we doesn't know that. Plus ammonia. Ammonia is a neutral complex. Neutral complex for neutral is neutral ligand. So its value is 0, which is equal to plus 3. The 6 is the 6 related to the 6 ligands. That's why I mentioned over here 6. So what is the oxidation rate of the cobalt? This will get cancelled. Okay, 6 into 0 anything is 0 only. So what is that? Plus 3. Oxidation state of the cobalt is plus 3. So first one is over. And the second one, what is the second one? Electronic configuration we need to know the cobalt, central metal atom. Okay, cobalt, what is the electronic configuration? How to write the electronic configuration? You know that very well. In a d orbitals, okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, this is the D1 to D10 elements. 1, 2, 3, 4, 5, 6, 7. What is that here? D7. Okay, this you should know that. Okay, this is the first D transition elements. The cobalt is, what is that? D7. Cobalt is D7. Actually, the atomic number of the cobalt is 27. So how to write the electronic configuration? Cobalt, argon 18 plus 3D74S2. Okay. So the oxidation state, as I mentioned earlier, it's a plus 3 oxidation state. So what about plus 3? What will happen? If 3 electrons are removed, then argon, here 2 electrons, here 1 electrons. Then 3D6. This is the second one, electronic configuration of the cobalt 3 plus complex. Okay, this is over. And the third one is, what we need to do? Third one is whether it is a weak field ligand or strong field ligand. We need to find whether it is a weak field ligand or strong field ligand. See, the ammonia is a strong field ligand. Ammonia is a strong field ligand. So if ammonia is a strong field ligand, what is the usage? If strong field ligand means the electrons pairing takes place. What is that? Pairing takes place in the electrons. If it is a weak ligand, pairing does not take place. So here ammonia is a strong field ligand. And you can ask me that. Okay, it's a pairing takes place. And how do you know whether it is a strong field ligand or weak field ligand? Another this thing also will be there. I'll tell you how to know that whether it is a weak field ligand or strong field ligand. See, all the halogen atoms like chlorine, bromine, iodine, these and all halogen atoms. So these are all weak field ligand. And cobalt, cyanide, ammonia, even water also weak field ligand. These are all the usually they used to ask as a ligand. Okay, and cobalt, cyanide, sorry, not so cobalt, carbonyl, cyanide, and ammonia. These are all strong field ligand. Okay, even you can see, if you to see the spectrochemical series, you can get the very clear approach about ligands, whether it is a which one will be the strong field ligand and which one will be the weak field ligand. It's an easy way to remember. That's why I mentioned these things. This is the most probably you will get it. Okay, and this is over. Okay, and the next thing, so ammonia is a weak field ligand. So what we have to know, this is the cobalt complex. In this, ammonia is a weak field ligand, and we know very well about electronic configuration also. The electronic configuration, argon 3d6. Okay, because of the cobalt 3 plus complex, because of cobalt 3 plus, argon 3d6. How to write 3d6? See here, this is the d orbital. 5 subshells are there. How electrons need to fill? Singly first you need to fill, and then you have to fill doubly according to the Hund's rule. Okay. This is 3d6. Okay. Now this is coordinated with 6 ammonia. And this ammonia is a which type of ligand? Strong ligand. Strong ligand means what will be the case? If the strong ligand means, if ammonia is a strong ligand means, then pairing takes place. So once pairing takes place, how it will be? See here, this will this and get pair, and this get pair. Okay, so the pairing takes place, and the remaining will be vacant only. In this place, which is going to give an electron, ammonia is going to give an electron to the cobalt, and the complex is forming. So this 6 pair of electron is going to given by ammonia. See, each ammonia ligand gives 2 pair of electrons. Okay, each 2 pair of electrons. So here 6 ligands are there. 1, 2, 3, 4, 5 and 6. 6 ligands are there. I'll mark it in a different manner so that you should come to know. These are all ammonia ligands. 1, 2, 3, 4, 5 and 6. 6 ligands. Each ligand gives, what is that? 6. Each ligand gives a 2 pair of electrons. So 6 ammonia is there. So 6 ammonia gives 12 electrons. Okay, this is the thing. What is this? This is a 3d orbital. This is 4s, 4p. Okay. So how you would be right? What is the hybridization now? Here a d2sp3. What is the hybridization now? The hybridization is, first thing what we need, what we have to find, hybridization. Hybridization. What is the hybridization now? D2sp3. The hybridization is D2sp3. Okay, clear. The first part is over. The second part, magnetic property. The magnetic property, how to find out means whether here all the electrons are paired. Okay, then it is diamagnetic. If the electrons are unpaired, then it is paramagnetic. Paramagnetic. After the ligand formation, how the electrons are, we need to check. If here all the electrons are paired, so the property is here diamagnetic. Diamagnetic in nature. Okay, and the third thing, whether it is an inner or outer orbital. See here, the d orbital is here. Okay, this d orbital is an inside. If it is sp3 d2 means that is outer. This is inner orbital. So this is inner orbitals. Inner orbitals. Okay, these are the 3 things we can get from the valence bond theory. Okay, so after this I'm going to say about limitations. Okay, what are the limitations are there? The first limitation, in this, number of assumptions are there. Okay, number of assumptions are there. That is the main failure of this. Okay, that is the main failure here. First one. And the second one, the magnetic data. Okay, they are not saying quantitative interpretation. Okay, they are not say about quantitatively about the magnetic data. Just they are saying it's a diamagnetic, paramagnetic. How much it is, that they are not saying. Okay, quantitative interpretation of magnetic data is not given. Quantitative interpretation of magnetic data is not given. Okay, this is the second one. Number of assumptions are there and quantitative interpretation of data are not given. That is the second limitations. And the third one is thermodynamic and kinetic stability of the complexes are not given. And kinetic stability. Thermodynamic and kinetic stability of coordination compounds are not given. This is also not there. And fourth one is, if the coordination number, okay, if the coordination number is 4, we know very well 4 ligands can able to attach to that. So the geometry is, can able to find out the geometry is tetrahedral geometry and square planar geometry. Okay, tetrahedral or it may be square planar. So this differentiation, why this is the tetrahedral and square planar, how it will be, this is not differentiated. Okay, difference is not mentioned. This difference, even though the same coordination number, which contains different geometry. Okay, this difference is not mentioned in this valence bond theory. Okay, and the fifth one, and the same way weak and the strong ligands. Weak and strong ligands are not distinguished properly. Okay, here the weak and strong ligands are not distinguished properly. It's not differentiated properly. Okay, these are all the 5 limitations in the valence bond theory. That's why we are moving to the crystal field theory. So we will see about the crystal field theory in our next live classes. Thanks for watching.